All right, so hopefully you have printed the packet of notes, or you at least have them up in front of you after this video. So whenever I list the homework like this and I don't specify, it means to look at the homework sheet and do whatever problems I have listed, because those are hand-picked problems. Now in chapter 27.2, I had to clarify because these are the only problems you should do from that chapter after this video. And whenever I say read, I really think that is helpful because some of the material is kind of hard, and it's always helpful if you've gotten some background on the topic before you actually watch the video, so then the lecture video will make a whole lot more sense. So read 28.3. But before you actually start watching this video, I would like you to take 3 minutes just to read this, which was part of the packet. It's about the topic of odds. So go read that and then come back. All right, so this topic of odds, it always sounds ruder when I complain on a video lecture as opposed to in person, but I'm going to complain about this topic. I'm still going to cover it. It is in your book, and actually it is part of one of the SOLs for the state of Virginia, one of the grades. The problem with odds is a couple of things. If you read what I asked you to read, they even talk about how, I'm making sure my video is okay. They even talk about how most people in the real world will actually use odds and probability interchangeably. Like, the odds of me doing well in her class are really high. And we know what you mean, but technically odds are a completely different form of probability. And for most people, there is absolutely no need to use the formal form for odds. The only people that use it are gamblers, whether it's sports gambling or Vegas gambling, because putting it in the form of odds helps determine how much your pay will be if you win. So that is the only time it's useful, and I'm pretty sure that none of us are professional gamblers. I always struggled when my kids were in elementary school because they would come home and maybe they had an odds problem, and I wasn't sure if the textbook really sort of just meant probability or if they really meant the true form of odds. Because I know, again, in real life, most people use those as synonyms, but they're actually not. So I'll show you the general setup, then we're going to do 3 or 4 little examples. You guys will probably like odds a little bit better than me, coming off of 107, 108. It kind of relates to the pictures that you guys got really good at drawing. So the probability of some event A, we would have a fraction, right? Well, we're actually splitting up the denominator as the numerator plus what is left over. Then you have to worry if they're asking odds for something or odds against something. So if you want odds for A, it's M colon. The colon is really critical. That's like the notation for odds. And if you want odds against, it's R colon, M. Now, we are going to do the problems like this, but I just want to show you what makes more sense to me. Again, this is a personal opinion, right? You can think about it as the probabilities and then reduce, and I'll show you what I mean. Probability of A colon probability of not A. And then odds against would be the opposite. So let's start with the easiest problem. Trying to come back to the pictures that I know you guys love. Let's say this is blue, 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 and green. Okay, the 4 pieces are equal, right? Equal area. So we know that the probability of blue is 3/4. Now, using this format, that would be 3 over 3 plus 1. So the odds, so the probability of blue is 3/4. The odds for blue would be 3:1. So see, look at this odds form. So many people think this is somehow like 1/3 or 3 or something like that. The odds for blue, 3:1, 3:1. If you want the denominator, you have to add up the 2 sides of the odds, right, to get that 4th. Now, this one was very easy because we can see 3:1, right? But maybe when the numbers aren't so easy, you don't feel like drawing a picture. Let me just show you a slightly alternative way using my probability. So since it said odds for blue, I can go probability of blue, probability of not blue. Okay, probability of blue is 3/4 colon, the not blue would be 1/4. Now you just have to reduce it. See, there's a special form for odds. They have to be integers. So you can imagine, it's kind of like algebra. Multiply both sides by 4. There's your 3:1. Let's do another one. So a lot of probability questions, even in K through 8 in college, deal with a deck of cards. I learned a few years ago that your generation may not actually know what's in a standard deck of cards. If you don't, go Google it right now. There are 4 suits and 13 of each suit, ranging from ace through 10, jack, queen, and king. So if that is unfamiliar to you, please take 2 minutes to go Google it. But what I also think is very interesting is the placement test for JMU. One of the questions is a basic probability question about a deck of cards. And they weren't really trying to test that you knew what was in a deck of cards. They expected that you knew that, and it was a pretty easy probability question. The math placement test is supposed to be on your honor, where you do not go Google anything. So I've often wondered how many students are getting that question wrong when it's not because they didn't know the probability, when it's actually because they did not know what was in a deck of cards. I have been trying to get the math department to change that question for many years, and I will continue to try. So we're doing a deck of cards. We're going to pick one card. I'm interested, so my event that I'm interested in is a king or a queen. Here's the question. We want the odds against getting a king or queen. We're going to do this a couple of different ways. I'm going to start with my personal preference. So against, we want to put the not king, queen probability first, colon, then the probability of getting a king or queen. There are 4 kings and 4 queens out of 52 cards. So I know that that is 8 out of 52. So that means 52 minus 8. The other 44 cards are not kings or queens. Okay, so I can multiply both sides by 52. Now the other picky thing about odds is you have to reduce. You would never see that on a gambler's website. So we can divide both sides by 4, and we'll get 11 colon 2. All right, so that's using the probability way. Technically using the odds formula. All right, well, let's let's pretend I haven't done that side. Let's pretend you were starting there. The probability of a king or queen is 8 out of 52. Okay, so which is 8 over 8 plus 44. Now the odds for would be 8 colon 44. The odds against, which is what this question asked, is 44 colon 8. And again, you still have to reduce. Divide both sides by 4. So there's your 11 colon 2. All right, let's do another one. I'm trying to pick the ones that I know are extremely common in probability chapters. They always love to talk about decks of cards, and they always love to talk about the roulette wheel, as if most of us have ever even had the chance to spin a roulette wheel. I know I have not. Luckily, they usually tell you what is in a roulette wheel, so you don't have to go Google that. All right, a roulette wheel. There are 18 red slots, 18 black slots, and they put 2 extra green slots in there. So I guess we have a total of 38 spots on the wheel, right? So we want the odds against red. So probability of not red, colon, probability of red. If you prefer to do this the MR odds formula way, you are welcome to. I'm just presenting it from that probability standpoint. So red, I have 18 over 38, which means not red, that's the black and the green, right? So there's 20 over 38. Again, multiply both sides by 38. 20 colon 18, divide by 2, 10 colon 9. And that's the odds. That colon indicates odds. All right, let's do one more. I stole this from the book. At first it looked complicated, but it's not. They were talking about a basketball player. Okay, the probability that this particular player makes a basket is 75%. So they're giving you the probability. Now this one is not in fraction form, right? It's in percent form. Hopefully everybody knows that you could so easily change that to fraction form. But what I want to present is, what if this wasn't such a nice fraction? How would you deal with this percent? So they want the odds for making the basket, not against. This one asked odds for making the basket. So I can go probability of making the basket, probability of not making the basket. It doesn't really matter. I can actually do 75 colon 25. That probably is going to be easier than turning it into decimal form, because remember, odds have to be integers. So all of these are integers right now. I just have to reduce them, right? Divide both sides by 25 and you'll get 3 colon 1. Obviously, if you started here and did the odds formula or even the probability formula, there's probably 4 ways you can do this question. I don't care which way you do it, as long as you get down to 3 colon 1. All right, so odds are its own little, very special but different form of probability, and that's why we have to cover it, because for some reason we do actually teach our kids that in the K-8 curriculum. Let's move on to tree diagrams. So this video is kind of handling 2 very different topics. See, probability is hard, and I think one of the reasons probability is hard is there's not one way to do it. Probability can, okay, take the same topic. We will present it in a much easier fashion to, say, 4th graders, slightly harder fashion to 6th graders, get all the way up to AP Stats, and we're going to present it differently, which is, of course, level with the college level classroom, right? So on one particular problem, there probably is 4 different ways to solve the problem depending on the level of the student. So through the rest of this video, I'm going to try to be making some of those tie-ins of, well, you could do it this way, but guess what? We're going to eventually do it this way. But chapter 28.1, tree diagrams. It's kind of like graphing and statistics. It is a technique that we teach kids to not only be able to get organized and see exactly what's going on in a problem, but then also to convince them eventually why a shortcut works, just so they don't just believe us because we're the teacher and tell them, oh, just do that and it works. We've done these tree diagrams to actually convince them that it works. So I'm kind of starting at the youngest level right now. The very special case. This does not apply to all problems, but when we're teaching younger kids, we won't do the hard problems. We'll do the easier problems, right? The special case is when each outcome is equally likely. So since it's called a tree diagram, you're going to have things called branches. This probably isn't going to make sense yet until we do our second problem. But on the special case, you don't have to label the branches. Let's say we are flipping 2 coins. They are fair coins, meaning 50-50, 50% head, 50% tail. That's what I mean by equally likely. One at a time. Okay. Let's figure out all the different things we could possibly get from our experiment of flipping 2 coins one at a time. Well, what about if we flipped a head first? Or we could flip a tail first, right? Those are the 2 ways we could flip our first coin. Now on the second flip, so this is representing the first flip, over here is going to represent the second flip. We could flip a head or we could flip a tail for each one of these. So let's put that together. We could have head, 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 tail, tail, head, tail, tail. This in and of itself is a fantastic exercise for the younger kids, because if you just tell them flip 2 coins, write out what you might get, most of the time they don't list both of these. They're just like 2 heads, 1 head, no heads, that type of thing. But there are 2 different ways to get just 1 head. It could have been head, tail, or tail, head. Since these were equally likely, this is called the sample space. I can just look at the sample space and know that each one of these is 25%. The only time you can do that is on the special case when it's equally likely. Now, I'm overkilling this a little bit. What about if we wanted to summarize, so I don't want to look at all of that stuff, right? If you make a little table of all the possible outcomes and the probabilities, this is called a probability distribution. That word is distribution. I know I'm getting very sloppy over there. Probability distribution. Fancy word for table. Let's say I'm interested in how many heads, number of heads you flip. You flip 0, 1, or 2. Well, 0 heads is just the tail, tail, right? That's 25%. Probability should always be written in decimal form. 2 heads, oh, there's only 1 of those, 25%. Remember, each one of these is 25%. 1 head, well, that's a case that's just 1 head, and that's a case that's just 1 head, right? So 25% plus another 25%. A really nice thing about probability is you can check your work to see if you've made a mistake. All probabilities add to 1 because that's out of that 100% the unit whole, right? So we could organize it like that. So that's the first level of probability, where it's equally likely There's no fancy labels. They just look to see they got 4 different things. Each one is 1/4. But that only works for equally likely. So let's up this a little bit more. Let's jump a grade or 2. And through this, I'm actually doing at least one of your homework problems. So we're going to do this one exact problem 2 different ways. See, the last problem we did with heads and tails, it was pretty short. There were only 2 coins. Our tree diagram didn't get too bulky, okay? Well, we've upped it to 3 balls now. These are extremely famous problems. They're always talking about different colored balls in a bag. So we have 2 red balls, 1 green, and they're in a bag, and we're going to pick 2, one at a time. Now, this is the most important thing. Make sure you read the homework problems very, very carefully. It's going to either be with replacement or without replacement. Without replacement means I pick 1 ball, but I don't put it back in the bag. Then I pick the other one. So, we're going to do the uncondensed version first. This allows me not to have to label the branches because I'm going to show every possible thing. Like, I know there's more red than green, but if I just think about this as red 1, red 2, and green, those 3 balls actually have equal probability of being picked, right? 1/3. So if I'm going to show it as red 1, not just red, but red 1, red 2, and then green. Okay, I could have picked one of those in my first one. Now remember, I'm not putting it back in. So if I've picked red 1 is not an option anymore. For my second flip, it's either red 2 or it's green. That was all that was left in the bag because I didn't put red 1 back in the bag, right? On this one, if I pick out red 2, well, he doesn't go back in the bag. So the only things left in the bag now are red 1 and green. If I pick green, well, he's not in the bag anymore. So it's only red 1 and red 2. Because I showed each of the 3 balls, I don't have to label my branches because each one of these was 1/3 each. Now let me just write out my sample space. Right? Each one of those is equally likely. So very similar to head tail, but you can see it's getting a little bit long. I know there's still only 6 things, but goodness, what about if they give me an example that has 10 balls in it? There's no way I'm going to write a tree diagram for that, right? This is still manageable because there's only 3. Let's just get organized though. Let's say, again, I'm interested in the probabilities based on how many reds there are. Now, this question, I don't really care if it's red number 1 or red number 2, just how many reds. All right. So, well, I couldn't have both greens, right? Because I only had 1. So technically we didn't need to list that. I just wanted to keep it consistent with the last problem I did. How many just have 1 red? This one, this one, this one. I don't have enough fingers. Those 3 and that one. 4 6. And now 2 reds. This one and this one. 2 6. I have not messed up because this is 6 6 or 1. So, all right. Again, getting a bit cumbersome, but the reason why I did this is, and the reason why we do this, and maybe I should clarify that, the reason why we show the kids the uncondensed version, usually only once, because again, it can get a bit tedious, is to show them why when we're going to do the condensed version in just a second, why that actually works. And they can compare the two and say, oh yeah, I got the same probabilities. This is helping them see every possible thing that can happen because it's uncondensed. It's showing every single step. Oops, but now maybe we're skipping a grade or two. We're going to get up to what we call the condensed version. And that means we're going to label the branches. We're going to be doing the same problem, that page 677, number 4, the exact same problem. But we're not going to view it as red 1 and red 2. We're just going to view it as a red ball and a green ball. So we need a branch starting before the first ball that we pick. So obviously, on my very first pick, I could pick red or green. Now remember how there were 3 balls total? 2 of them were red. So we have to label this branch 2/3. There was only 1 green ball out of the 3. We're going to label that branch 1/3. Now, after we pick out a red, our second pick is either red or green. Now think about it. So this is where you have to go pretty slowly because this was without replacement. That's the most critical part of this problem. If I have picked out a red, that means there's only 1 red left. Well, let me back up for a minute. Once we pick 1 ball, that means we only have 2 balls left, right? And because I picked out a red, there's only 1 of the 2 balls that are red. My green's still in there, so 1 out of the 2 balls that is green. Let's do this guy, make sure we're okay with that. If I've picked out a green, well, he's gone. So the 2 balls that are left are both red. I'm overkilling this. I'm calling that 2/2 probability. Yeah, because there's no way I could pick another green. I've already picked the 1 green. Green doesn't exist. This is a probability of 0. I want to pause here because these branches are the first spot where students make mistakes. I apologize that I don't have a different color marker, but I want to show you how you can check your work. The branches, as you go, have to add up to 1. See how that adds to 1? See how that adds to 1? See how that adds to 1? That's a nice check to make sure that you haven't made a silly mistake. Now, here's the really cool thing. Well, let me write out. We had red, red. We had red, green. We had green, red, and green, green. Since we did it like this, they were not equally likely. We had to label the branches, so you can't say that each one of these is 1/4. That does not hold. You have to multiply your branches. 2/3 times 1/2. Hopefully you know how to multiply fractions. 2/6. This one is 2/3 times 1/2. Another 2/6. This is 1/3 times 2/2. Another 2/6. And this is, of course, 1/3, maybe I should write that, times 0, which is 0. And look here, if you've done it right, that should add to 1 or 100%, right? 2/6 plus 2/6 plus 2/6 is definitely 6/6, or 1/3, 1/3, 1/3, definitely 1. So the reason why we do the uncondensed earlier is so then the students can compare and say, yes, we did get the same thing. Let me show that probability distribution. Sorry, I erased a little bit too much. Okay, 0 red would be all green. Oh yeah, that's 0. 1 red. Both of those, right? 4/6. And the 2 reds is 2/6. Yes, I'm at 1. And this matches exactly what we got on the uncondensed version a minute ago. So you can kind of see that level of progression from the special case where you don't have to label branches to the uncondensed version which can get a little bit long if the problem is long. Sure, you don't have to label the branches, but it's getting very tedious, to the condensed version. And your book, well, it's somewhere in chapter 28.2, does go through a condensed and an uncondensed version, so you can see more examples in your book. All right. Oh, yeah, sorry, before I make you do one. So those are all tree diagrams. Again, a bit tedious. Guys, I don't do a tree diagram in real life. So let me show you where we're eventually going with this. So now we're up into like high school level. So we're doing the same problem. So it was what? 2 red, 1 green without replacement, right? I haven't switched problems. I'm just switching the way we solved the problem. Let's say they ask, what's the probability of red, red? 2 reds, right? You could look back through your notes. We've already decided it's 2, 6 from lots of different ways, from the tree diagram. We're not doing the tree diagram. So how are we going to do it? We're going to use what I call sort of informally the dash method. I need a red on my first grab, and then I need a red. Okay, there were 2/3 that were red on my first pull from the bag, right? Remember, this is without replacement. So I only have 2 balls left. And I used up one of my reds, so I must only have 1/2 left. There is that multiplication you saw just a minute ago on the tree diagram. But you don't, if they're only asking for that question, why do the whole tree diagram? Why not just work on the specific case that they've actually asked you? All right, let's do one more, or one more little piece. What about if they asked red, green? Okay, I need red, then I need green. All right, red, we know there's a 2/3 chance, but now I've removed a red, so I only have 2 balls left, but I still have my 1 green in there. So again, this is 2, 6, or 1/3, or of course 33.33%. I'm being lazy. Oh yes, the book shows condensed and uncondensed on page 670, if you want to see more about that. Now, when we're in the classroom, I get to make y'all work on something, right? By yourself or in groups, and then I walk around and help people, and we do that for like 15 minutes to give you a sense and an idea of how you are on this topic and, you know, which mistakes you're going to make and that type of thing. That's where the true learning occurs. That's kind of hard to do on a video. So right now I am going to ask you to go do a problem. I do want you to pause the video, try it yourself, then come back and watch the answer on the video. That's the only way for this online learning to really work, is for you guys to try things when I ask you to try things by pausing the video. So let me put up what I'm going to make y'all do. And again, pretty sure we're doing a homework problem. Okay. So now we have 10 balls in a bag, and that is really to encourage you. You are absolutely not doing an uncondensed version. If you were to try to do that, you'd have to have red 1, red 2, red 3, red 4, green 1, green 2, green 3, green 4, green 5, green 6, etc. No one wants to write that much. So what I want you to do now is a condensed tree diagram. Work it all the way through where you're multiplying your branches, where you then have the entire sample space with the probabilities that, if you've done it right, should add up to 1. Make sure you do see it's without replacement. Okay, so pause me and then come back. And this is why I did not put the answer on the notes, so you could give it a try and not have a hint on it first. All right, so let's see how you did. Kind of awkward fractions, I'll be honest. I'm going to keep the fractions the whole time. Normally I'm a decimal fan, but on this problem, the decimals are so awkward, and then with rounding error, it can look so much messier. So, I could have drawn a red, or I could have drawn a green. Now, there are 10 balls total, so you should have for the red 4/10 and for the green 6/10, right? And there's my 10/10. There's my probability adding to 1. So now we know that that's the next thing that can happen. I'm prone to making silly mistakes also, so let me show you something I do. Since this was without replacement, I know on the second draw I only have 9 balls. So I go ahead and make all my fractions out of 9. So I don't forget that I'm not out of 10 anymore, I'm out of 9. All right, if I picked a red, then I only have 3 reds left. But if I picked a red, I still have all 6 greens left. And look, 3/9 plus 6/9 is 9/9. That equals 1 right there. Good, I haven't made a mistake. All right, let's do down here. If I picked a green, I still have all my reds left, right? All 4. But if I picked a green, I don't have 6 anymore, I have 5. Yeah, and there you go. There's that 9/9. So I have not made a mistake. So we've got red, 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 green, and maybe I should put a little line here. Green, red, and green, green. Now we just have to multiply the fractions. Remember, you're just multiplying numerators and denominators. 12/90ths. We can reduce later. 24/90ths. Awkward to say. 24/90ths. 30. And I'm going to check my work again. 54, 64, 74, 78, 80, 90. Yes, that is 90 out of 90. And yes, at this point, you are welcome to turn those into decimals. Didn't bring my calculator. Well, I can use my phone. I don't have my 90ths memorized. Hold on. 12 divided by 90. 0.1333. 24 divided by 90. 0.2667, right? Because I want 4 decimal places for probabilities. So make sure you're rounding that to 0.2667. Of course, you could change that to 26.67%. That is not 27%, and it never will be in my class. If you want, you can say 26.67%, or you can leave it in decimal form. So this must be the same thing. Because I don't trust my mental math right now. Oh my gosh, I can't believe I just put that into my calculator. Okay, 0.3333. And sure, there'll be a little rounding error, but if you add that up, yes, you should get approximately 1. All right. Now let you try one more. Again, doing another homework problem. Oh, this is, hold on, don't want to misspeak. Oh, same problem, but with replacement. Where we have 4 red, 6 green, but it's with replacement. So it's just exactly what you did, but with replacement. Actually, this one should be a little bit easier. You can pause it and try it, then come back. All right, so 4/10 red, 6/10 green. Nothing different so far, right? But I put it back. it's with replacement. So red is still 4/10. Green is 4/10. Red is, oops, green is, how about 6/10? Red is 4/10. Green is 6/10. See, they didn't change here since it was with replacement. So red, 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 green, green, red, green, green. Multiplying the branches, 16 out of 100. Since this is out of 100, it's really nice, 0.16%. 24 out of 100. 24 out of 100. 36 out of 100. And of course, that adds to 1. So hopefully that was pretty easy. I want to summarize it into a probability distribution and then remind you how, at some point when we're not doing tree diagrams, how you're actually going to do this problem. I'm going to leave that part up just for a second. Okay, 0 reds would have been all green. So I took care of that. 2 reds is right here, the 0.16. And remember, 1 red, there are 2 different ways to do it, so you have to add those together. So that would be 0.48. Okay, and of course that adds to 1. So now let me get rid of this. So this is just a way to organize the entire problem, right? But again, sometimes we don't care about the entire problem. They're just going to ask some very specific questions. So we're doing the exact same problem. We're just asking from, well, maybe I should write that. We're still doing the 4 red, 6 green, with replacement, where we're picking 2, okay? But let's say they didn't say show the entire sample space, show the entire probability distribution. Let's say this is the only thing they asked. Probability, the first is red, second is green. They're telling you exactly what they want to see. They want to see red on the first, green on the second. Okay, red, 4/10, green, because this was with replacement, so I get to keep my out of 10, 6/10, 0.24. Here is one slightly trickier, and it's helping set up for the next video where we start to do word problems that don't necessarily have to do with red and green balls, but I swear to you, it's all the same concept. But as soon as I turn them into word problems, students tend to not like what we're doing. So, how about, what's the probability you get just 1 red? Now, I want you to compare these two. See how that was very specific? They told me exactly. I didn't have a follow-up question. First is red, second is green. Fine. Now, this one is kind of vague. Probability I get just 1 red. Well, I don't know what you mean. Did you mean the first was red and the second was green? Or did you mean the second one was red and the first was green? See how there are 2 scenarios that satisfy this? And if you look back at the tree diagram from a few minutes ago, you're going to see how both of those came up in the sample space. So I have to do both cases. Red, green, green, red. And here's that 0.24 plus 0.24 or 0.48, which we had filled out just a minute ago looking at our tree diagram. So the tree diagram really is just to convince you when we start doing the shortcut way of students are always like, well, how'd you know to add or how'd you know to multiply? That's what the tree diagram has shown you of why this process works. These processes right here are special probability rules, and we gave them names, and that's what the next video is based on. So again, that progression of with the younger kids, showing them easy tree diagrams, medium kids, showing them the harder tree diagrams, college level, next video, give you the probability rules, and we're going to start doing it this way. So you do need to know all levels of it. All right, try the homework that I assigned at the beginning of this video. and then you can move on to the next video.